Thank you for the kind introduction. Ladies and gentlemen, good afternoon. I'm pleased to see that because of the online modality of our presentations, there are a lot of visitors that we normally do not see in Witbank. For example, some of our Indian friends that I know very well, I see have joined as well. So from my side, sincere welcome to everybody. The work that I'll be presenting this afternoon is really the work of Nikki Hughes. She is a PhD student, and dry coal beneficiation is a topic. And I would like to then at this stage just recognize my co-authors, which is Nikki Hughes, Prof. Marco Leroux, who you know also very well, who's a supervisor. And the order in which the authors present themselves, or the names of the authors are listed on the first slide, is no accident, because I'm the messenger, and I will be presenting the work that was actually done by Nikki Hughes. So she's got to take all the credit for this. Also, some of you may note that this is the same, blatantly, the same presentation I gave at the Australian Coal Prep Society a couple of months ago. It went down fairly well there, and I think this certainly makes for some interesting information. So let us look at the current dry coal beneficiation techniques. The outline of this talk will be just looking at the review paper. The whole talk, or the whole presentation, is built on a review paper that is going to be published very, very soon. There's a lot of information in the review paper. It's quite extensive, so there's no way that I can present everything. So what I'll do is I'll just have some snapshots of types and examples of dry processing, and then for one or two of them, we will be looking at the performance and the operating parameters, also what the limitations are, why we're battling with dry coal beneficiation. Now, I'm preaching to the converted, I guess, here by saying that there is an interest in dry coal processing because of the problems and the costs normally with post-processing dewatering and wet waste disposal. There are all sorts of water constraints in arid regions, and even if there is water, so there's a whole move away, or there's lots of motivation to move away from wet processing. Maybe it is a bit of a pipe dream, but still it's happening, and there are people around the world who's making it happen. Of course, there's this environmental pressure as well, something that we're all acutely aware of, that we need to move away from just simply wasting and dirtying all our water. So we need to balance the advantages of dry coal beneficiation against, and these are the problems that we normally find. There's generally lower efficiencies, especially for difficult coals. South African coal, notoriously difficult. And there is no way that we can currently get to the efficiencies that DMS or wet processes give us. Dust is a problem, or it can be a problem as well. And then feed size limitations. We can fairly effectively and efficiently dry beneficiate, for example, with X-ray technology, larger particles. But there is a size limitation as to how low we can go. And I will be addressing some of that as well in the presentation. So the efficiencies and the throughputs especially are still not on par with wet beneficiation, classical wet beneficiation. So at this stage, the development of dry beneficiation is really driven by the lack of alternative options in extreme environmental conditions. If you're running in an arid or a dry area, you have no choice but to look at dry beneficiation at least, and that is what's driving the research. So at this stage, there is some dry beneficiation around, but it's mainly used for pre-concentration or for scavenging. It is not, in general, it is not the norm. I know of in Mongolia, for example, there are quite a few dry plants, but in South Africa, certainly not. So some of these technologies are well established, others are unproven and novel. And I like the word novel because it means that people are working on these at the research level at least, and that is a good start. Now, it's nothing new, of course. If we look at hand sorting, raking and picking machines have been used for decades. So those were the rudimentary or the fundamental dry beneficiation processes, even though we know that it's not very efficient and not very economical. Even the first pneumatic tables and jigs appeared in the in the mid-1910s. But then dry processing declined, and it was really due to the surge of wet dense medium separation, especially in cyclones. It became so easy, so cheap, and so efficient to run these wet DMS cyclones and other DMS machines as well. So by the late 1980s, very little dry cold processing was in operation because there was no need for that. There was no economic drive, and certainly not an environmental drive. So nowadays we've got the newer developments now. Fluidized bed separators are coming back on, upward cyclonic suction treatments and winnowing. I'll talk a little bit about those in a little bit more detail. And then on the finer side, to go for the fine particles, you can consider electrostatic and magnetic separation, although this is still far, far, far away from economic implementation. Now, when looking, again, this is a research paper or a literature study, and the information that I'm presenting here is limited to the type of information one can get from the public domain. So while there are companies maybe that's got some reports and some nice work on dry beneficiation, obviously not all of this is accessible to the student. So what I'll be presenting are from research papers in the public domain in open, and these are just some summaries here. So in general, one can divide your dry processing in a few big groups. For example, comminution and screening, that's a it does some separation, and it's really it is a dry beneficiation system, although classically we don't say it is. Sensor-based sorting has been well developed, and we've had a lot of presentations even at this venue or these events about X-ray sorters, and they seem to be working very well, and they seem to be in their niche, and that technology is well developed and well presented. Then gravity and density separation, which is a little bit of a problem, and we'll come to why. And then finally, magnetic separation and electrostatic separation, which is really not, it's at the research level mostly. Right, so these are the 5 types, and we'll look at each of these in turn. Now, sensor-based sorting, once again, I don't want to say too much because we all know the X-ray sorters, we know how they work, and they are already established in the industry. So it works with mostly dual energy X-ray transmission, and it works on the difference in X-ray attenuation that differentiates between the denser and the lighter regions, because the denser regions absorb more X-ray energy. And if you're going for dual energy, it means that you can compensate for bed thickness or sample thickness on the belt. And the detectors normally consist of an inline scan camera that converts this image into a grayscale digital image, and there's some intelligence around this, and then some actuation, whether it be flappers or pneumatic, is then actuated based on some threshold value. This is more rock and this is more coal, and therefore the actuator makes a decision there. It's nothing new. I was tempted to say it's not rocket science, but I think the science behind these things are quite phenomenal. So that is a way. Now, these things really work on larger particles, and this is from the literature. This is a range of performances. Now, again, don't hold us, to some of these numbers, because you will notice that the numbers, especially the performance parameters at the bottom, range over a fairly wide range, and these are the numbers that were presented in literature. So one can get EPMs of pretty low, 0.04, and then ranging up to 0.3. The yields are from medium to actually very, very good. And the cut points, and that is one of the reasons, one of the issues with this is the cut points tend to be on the high side. Low cuts is becoming difficult with the sensor-based technology as well, because you are depending on the ash content, the minerals in the coal to attenuate some of the X-rays. And if there's not a lot of minerals, then suddenly that correlation does not become that clear. So moving on to gravity or density separation, this is exploiting, again, the science behind this is quite well known, exploiting the differential movement of a particle in a fluid, and in this case it is air, and we're comparing the gravity forces versus the viscous drag and the buoyancy that keeps the particle up. It is affected by particle size, particle density, and even particle shape, especially in air. And the medium type density and viscosity, these are all factors that play into this. Now, if you do this in water, it's a little bit more straightforward. Because of water's density and viscosity, you reach, your Reynolds numbers are lower than for air, for example. So to do the same separation in air is very, very tricky, because you move into a turbulent zone fairly quickly. One can think that to separate things in a swimming pool versus an upward flowing stream of air, it's two totally different. It's the same mechanisms, but it's two totally regions that we are talking about. So it's not that easy, but it has been done. For example, air jigs, pneumatic oscillating tables like the FGX, SEP Air, which I'll talk a little bit about just now, a very exciting new technology that's just been imported or investigated in South Africa by Coltech. And then air dense medium fluidized bed separators, that's the dry dense medium fluidized separators. It used to be very popular in China. It was developed in China. How far are we away from that? And then of course others like winnowing, which I'll talk about, and then dry reflux classification. That's an interesting one. I'm only aware of one PhD on that, where they looked at dry reflux classification. We all know the reflux classifier, but in this case we're putting water through, air through it and not water. But it has been looked at. So on elutriation and jigging, we've got the air tables, the air jigs, and the pneumatic oscillating tables in there. So what happens is you've got a fluidized particulate bed, and in this, with either jigging action or maybe just a normal lifting of the bed, you've got hindered settling and consolidation trickling, and you end up with a particle stratification where your denser particles, the heavier particles, will sink to the bottom of the bed, and then, like in a normal jig, you just need to separate them somehow with cutters or ports or something like that. So again, the technology makes perfect sense. It can be a continuous or a pulsating flow. If it's pulsating flow, obviously it's a jig. And it can have some vibration added to it or inclination to it. These are all different technologies. And when we look at the paper that's coming out, all of this will be well described there. You also get bead depth separators, like the jigs where you have a fairly big, deep bed. And the air tables, on the other hand, have this shallow table. So it's two slightly different mechanisms, where the one is flowing in air and the other one is more of a settling striation, consolidation, trickling mechanism that does the separation. And you have either countercurrent flow of product and discard, like the all-air jig, the ACO flow, or you've got the countercurrent, like the flow of the two products, the product and the discard, like the air table, FGX and the KAT. And again, the details about these things are available in literature. I've got all the references on the slides as well, if they are distributed afterwards. So again, these are just pictures, and it's quite amazing whenever somebody presents something on dry beneficiation. I've seen this at least 3 times this year. We use the same number, the same pictures, the same graphics, because these all come from papers that's all around, and it's well published as well. So these pictures of mine come from other people's work. And again, this just you can go into the details and have a look at how these things work. But there again, there's a list of the types of machines that we are talking about. Some of them are good, others are probably not that good. Now, how good are they? Again, this is a table of the performance, and it ranges widely. The one thing that just jumps up at you from this slide is the particle size ratio, and this is really catching. This is one of the things that we are battling with in any gravity separation, and especially in dry beneficiation, where you use air rather than a medium, is that you are limited to the particle sizes that you can separate at any one time. And if you look at settling theory, it's very clear that the relationship determining how fast the terminal settling velocity of a particle in a fluid, whether it be air or water, is linearly related to the density. In other words, if I double the density of a particle, I will double the settling velocity, but it is a power cube to the power 3, in other words, cubed to the size. So the particle size can just change a little bit, and the behavior of the particle changes completely. It's very, very sensitive to particle size. And that is one of the takeaways of dry beneficiation for most of the machines, is that you must have proper size control before feeding the machine. Now that brings other challenges, of course, like dry screening, which we know that we can do that, but again, not a lot of work done. Well, there's work done on that, but I don't think we've been successful in really nailing dry screening, especially to very narrow particle sizes. So that is the one thing that we need to note here. The All-Air Jig claims that they can do a 10:1 particle size ratio. Again, I'm just repeating the numbers. And then the second one from the bottom is the air dense medium fluidized bed. That's the dry dense medium. They can do a 10:1 ratio as well, which makes sense because in a dense medium, your particle size becomes less important. Think of cyclones as well, where you can, in a DMS cyclone, you can virtually send the entire feed into it in one go. So it's not sensitive to particle size there, but all the others, you've got a sensitivity to particle size. Now, the particle size distributions that it can take, again, there are Airtable claims to be able to do less than 6 millimeters, and so can the KAT, the Akka flow. But it's not often that you see FGX, for example, below 6. It doesn't really like it. So again, one can see this limitation coming in with particle size, although some of the machines can do it. And then the capacities, well, that's quoted there, but I can't really comment on that because it depends on how big the machines are, and it depends on the difficulty of the coal and that sort of thing. Just a little bit on the SACPS, and this is a separation machine that was developed in Russia. Some of you in the audience might be aware of this and familiar with this. I'm personally very excited about this development. I think it's actually a very, very good machine, and it works through an upward suction through a mesh conveyor belt. So you've got your coal particles on a mesh, and it's like a giant vacuum cleaner on top, really, and it sucks the particles up. And of course, as it sucks the particles up, those with the higher densities will tend to stay behind, and the lighter ones will be lifted. Now, there's some tricks in this as well, and that's where the IP lies in the SACPS, and that is the generation of the vortex that lifts the particles up. You've got to be very, very careful to control the flow. It must be equal flow, equal velocity, and very laminar flow and equal flow lines as well in the same direction. But that's been done, and it's been done at industrial scale. Mostly in the iron ore industry, and as far as I know, the first applications of this was in South Africa, where we had a unit like that recently. It's still here, but there's some tests done recently, and anecdotally, the test went very, very well. The Coltech report is out with the permission of the hosting companies, but that data hasn't been, I haven't had the chance to work that data in here. So it's an upward flow. So the small light particles are lifted first and the heavy ones stay behind, like that. It's just, again, important to note that it separates by size and density. And once again, we have this need for a narrow particle size to be fed to this machine. And of course, particle shape, that's an interesting one. Particle shape also comes in here. And if all of your coal is fairly rounded, then it seems to be okay. But if you start getting flaky, flat, slabby particles, then there's all sorts of as well, because one can think of the leaves from the sycamore tree, the helicopter tree, syringa, by the way, and how it behaves in air, and it just spins around and it does anything. So that's something that one must consider, not just the size, but also the particle shapes. So in this case, we are combining, or the Russians have combined the pneumatic separators and the vortex technology, which I said is the IP behind this one. There's some interesting or very nice data here that EPMs look fairly reasonable. They quote a 1 to 100 millimeters, but I think that's not in one go. What they would normally have is 3 or 4 of these in parallel, each separating a certain fraction of the size. And again, we're talking about dry screening then ahead of that. These won't work unless you've got very efficient dry screening. The cut point densities seem to be a little bit on the high side, so it looks like more of a destoning, de-ashing application. But the product yields, again, pointless to say anything unless you know a little bit more about the car. As I said, the Coltech data is out. There's a report on that. Some of you might have seen the report. I haven't built those numbers into the slide either. But it certainly looks very, very promising, even for South African cars. Then the Chinese development of the dry dense medium separation. There was a lot of interest in this some time ago, and they had absolutely huge plants operating. And for some reason, and I'm under correction here, but for some reason this sounds as if it's fell into disfavor. And there are a couple of reasons that were quoted why this technology didn't really go to the full commercial scale that we thought it would. It uses an upward flowing air in a dense medium like magnetite, but obviously here you want the coarser magnetite. So it fluidizes a magnetite bed like a normal fluidized bed, and then the coal is added into that. And the fluidized bed then acts as a medium, a liquid medium, similar to a liquid medium where your heavier particles will drop to the bottom. It makes perfect sense if you look at it from this way, from the science and the physics. It certainly works very well. Again, because we're working with air, it's very difficult to not stir the bed up again. In other words, moving into a turbulent regime and then get back mixing again of the particles after. So the control on this one is pretty tricky, I would think. So the coal is then separated into sinks and floats, and then of course you need additional processing to remove the magnetite from the product and the discharge. That can be done by screening because the magnetite is fine and the coal is a little bit coarser, and you have to recover the magnetite. Obviously, there's a lot of contamination then of the coal fines, dust and things like that in magnetite. And unless you're going to wet it or have very large capacity dry magnetic separators, you got a problem. You got to think about how to remove the magnetite or not have too many magnetite losses from both the product and the discharge streams here. That makes it a bit tricky. So there were some improvements in the technology since its development. So they went for deeper beds, they added some vibration, magnetically stabilized beds, and dual density beds where you had 2 densities in the same bed, improving the separation. But the numbers that were quoted, very, very impressive EPs, and of course the cut point densities could go right down to very low cuts, 1.3. And again, these are Chinese numbers, and I see some Indian colleagues also done some work on this. And as I said just now, for some reason I heard that it had a lot to do with the moisture in the coal. You can imagine if you've got a little bit of moisture going into this bed, it's just going to choke up. You're just going to form globules. Magnetite is easily wettable, and it just forms these clots, and you've got all sorts of problems. So your moisture control into the plant is crucial, as with most dry beneficiation. Now, winnowing, and this one I know a little bit more about, and because this is the project that we are running, one of my students. And we all know the winnowing concept is where the farmers would take some wheat and they just throw it in the air, and then the wind would carry the chaff around, and the wheat will fall to the bottom. So it's using a horizontal air flow to displace particles according to their density and in their shape in a certain sense as well. So it works mainly on a density difference, and the lighter particles are then carried away. If you look at the picture, the graphic on the right, you can see the typical displacement of a particle if you drop it in a horizontally flowing air. We've been able to model this now fairly accurately, so we can predict very accurately what that distance x at the bottom will be, how far for a certain size of certain airflow and density, how far that particle will fall, and that is the purpose of the topic of a PhD. It was cleaner. And we can run it either as a suction system, which of course solves your dust problem, or a blowing system. But in the end, we went for a suction system because we think it'll be better once you commercialize this, that you won't have a dust issue, or less of a dust issue. What we did here, these are results of 1-by-1 pieces of coal that we put into this one, so it's by far not commercial yet, but it just shows the degree of control we have over this. We can set the cut point at fairly low, fairly high. That's quite nice by just changing at the bottom. There are wedges, and by moving the wedges around, you can catch either the low or the high. You can differentiate between the low and the high density. And by predicting where the wedges must be, we can actually once again, it's a sized system where particle size is very important, but it shows promise. And because it shows promise, we went on to the PhD study where we're going to busy building actually. Some of these things are finished already. A demonstration unit that should fit on the back of a truck. And what we decided to do there was to separate the nozzles on top. There are size separation nozzles. In other words, we're using a similar technology than SACPS. It's not the SACPS, but it's a similar technology where we suck the lighter particles off first and then increasingly suck off the coarser particles, and then we have a fairly narrow PSD that goes into one of these density separation boxes. So air being sucked again on the right hand side with those pipes, suction system, and the particle falls in and it is displaced in the box. And we went for very narrow boxes because of the need for as close to possible laminar flow in these ones. Now this is not what the final one looks like. It's been reviewed a few times and we made some changes, and we are at the moment running some tests to just clarify and just to confirm that these components are actually doing what we want, and we'll start building the machine towards the end of the year. Middle of next semester we should have something up and running. We're very excited about this one. We are not the first and the only people to look at the winnower. SACPS in India published a paper some time ago. This is actually a running winnower. It is also a demonstration plant. And once again, the numbers look very good. The EPs are very, very good, in fact. These published results show that it's a fairly high cut point. So again, it's a destoning one. But even that makes a lot of sense. So winnowing technology, watch the space is what I would like to take away from this. We're all working on it, and I think it's very exciting. Now, I'm going to not go into too much detail on magnetic separation. Well, not any detail at all. SACPS, electrostatic separation, and the reflux classification. But when this presentation is circulated, you've got all the references there. So if you're interested in some of these, you can go for it. The magnetic and electrostatic separation, of course, needs to be. You need to go to much smaller sizes. So you have to pulverize the coal for electrostatic separation to be effective, by the way. So it's outside of the scope of, I think, what we're chasing for at big scale thermal coal preparation or export coal preparation. But if you want to go into ultra cleaning of coal, then certainly magnetic and electrostatic separation is the way to go. Now the limitations, I said before that direct coal beneficiation, there are lots of things stopping us from using it, or at this stage at least. Destoning tends to work very well. Beneficiation, you start getting into trouble, and the reasons for that is the near dense material has a huge part to play, the unliberated particles. Also, most of these machines, the cut points are fairly high on the density range. So yes, for destoning, proper beneficiation, a little bit more tricky. But the magnetic and electrostatic processes are not affected really, because you have to go crush finer and you have higher liberation, and therefore you can easily get a black-white cut on those technologies. How useful that will be in a mineral environment, mineral processing environment, I'm not too sure. But the particle size and PSD are two of the other limiting factors here as well. Density separation only works for narrow size ranges, and especially dry density. So you need to pre-screen on size, and you need to dry pre-screen on size. Many machines cannot really go beyond or below 6 millimeters. So you've got a top size, not too serious, but you've got a bottom cutoff as well. And you will often find that the application of dry beneficiation at this stage is really in the 6 millimeter plus. And for X-ray technologies, even larger than that. Finer coal is mostly at the early developmental stage, where you can go down to 45 microns if you want to. Not sure what you're going to do with 45 micron coal dust, but yeah. The feed moisture, that's the other one. It affects the unit operability and efficiency of all dry systems. Typical surface moistures, and we've seen this time and time again in our research, is that there's a magic number between 3 and 7%. That's surface moisture. If you can run in there, then you tend to be okay, because the coal is free flowing at that stage. It depends a bit on the coal as well, but most coals you can run with a 5% surface moisture, and the coal will not be sticky. It will not be sticking against each other and not against the vessel sides, for example. Some of these, the X-ray technology can of course tolerate higher moisture, FGX and the others, provided that your material is still free flowing, and that the fine material, which are the ones that become sticky at fairly low moisture levels, that is limited. So if you have a fairly coarse feed and it's still free flowing, then you can tolerate the moistures that's talking about. We all know that moisture becomes much more significant if your coal is finer, because of the adhesion of particle surfaces and agglomeration that causes entrailment, misdetection, and particle misplacement. it also affects the magnetite beds, as I said before, the dry, dense medium beds. Apparently, the moisture, it's not just the coal, but it's actually the bed itself as well that becomes sticky. Same with the autogenous fluidized bed like the FGX, although it is a little bit more tolerant. So in conclusions then, there are dry coal beneficiation technologies and they benefit environmental and even though I did not present any economical data, it seems as if the operational cost is low, and there's a case to be made for that. And I don't want to comment too much about it because these costs that we have are in the public domain, and I'm not sure that they always give the right picture. So I will not. I hesitate to make a call on that, but I am told. And we read that operationally these things, the processes tend to be a little bit more costly, both in capital and in operational cost. So the limitations are then feed coal washability. You don't want difficult coal. Obviously, the easier the coal, the easier the separation. You've got a particle size and a particle size distribution. You don't want coarse and fine mixed together, and you don't want your total feed to be too fine. And then, of course, a moisture content of between 3 to 7% seems to be ideal. So coal preparation practices are being forced to adapt. We are at least being forced to think about adapting to drier beneficiation as the resource and environmental constraints are building up against the operations. And it is our premise then that commercial and environmental factors will be the main drivers for the development, research and development and implementation of these dry coal beneficiation technologies. Ladies and gentlemen, with that one then, thank you very much. And Chair, I think we are open for questions.
Thanks, Quinton. Very, very informative and very educational in terms of dry processing. I think with South Africa not necessarily being a very high rainfall country, I think potentially these technologies will benefit South Africa. Just a few announcements before we open up the floor for questions. Just got two announcements to make. I think in the coal industry, we've had two giants in the coal industry fall. Recently, we've heard of the passing of David Michael. He was a stalwart to the SACPS and was a past chairman and past Coalman of the Year, as well as an honorary member. So we send sympathies to his family with regard to that. And recently, we've received news of the passing of Mr. Rajkumar Sachdev. He was the chair of the Coal Processing Society of India. So we wish him and the society, we wish his family and the society in India all the best in this trying time. So hopefully things progress better for them. I'm going to open up the floor for questions. So give me a minute just to open up the mics for everyone. So please, if you do have a question, please raise your hand and I'll acknowledge, and then we'll take questions. So the floor is now open for questions. Okay, give me one sec. Okay, so I'm waiting for, so I see there's no questions at the moment. So please, if you do have any questions, please raise your hand.
Chair, I see there was one question.
Mark Creswell.
I think from Guri Charan.
Okay, I think we'll get through that. I think, Mark, you've got your hand up. Please go ahead.
Can you hear me? Can you all hear me?
Yes, we can.
Oh, okay. Yeah, I'd just like to make some comments on your very interesting paper, Professor. It was great. I always remember many years ago meeting someone who witnessed one of the very last dry coal processing plants in Europe. This was somewhere in Spain. And he made this comment, which always stuck with me, that he could see the plant from about 20 kilometers away for the dust, and he could hear it from about 3 or 4 kilometers away.
They're sitting together. Mark Creswell is here.
Sorry?
Sorry, sorry, could you please mute if you are not?
Oh, 60 people.
Okay, sorry, I've muted them, so please go ahead, Mark.
So yeah, I first just wanted to comment that I met someone many years ago who'd seen this plant in Spain, and his comment was that he could see it and hear it from absolutely miles away, and he never forgot this. So goodness knows what the conditions were like inside the plant. I can dread to think. But I'm really pleased that you know, this technology is getting away. Now, my first comment is I'm an absolute believer in the narrow size range. So this 2-to-1 optimum doesn't worry me in the slightest, because the obvious solution, as you said in your presentation, Professor, that we just have parallel circuits. We just stick to that rule rigidly, and if we want to process 100 by whatever 1 millimeter, we just stick to the 2-to-1 size range, and therefore we end up having maybe 10 machines instead of 2. Okay, that obviously means extra expense, particularly in terms of distribution, but that's something we have to live with, because I think you've got to eliminate that size. You've got to eliminate one of those factors, and size is the easy one. So that doesn't worry me. The second point, moisture, and you talk about the 3 to 7% optimum range, and to me that also doesn't sound too bad. But the key there surely is we have to have raw coal stockpiles. But if we have stockpiles, we know we can approach 7% in, you know, a lot of conditions. Maybe not in the absolute middle of the summer rains in South Africa, but under a lot of conditions we can get to that less than 7%. So I would therefore advocate that these plants must have raw coal stockpiles. So oh yes, and my final point is with all of the, I really like that. Oh yes, no, a couple of more points. The SEP Air from Russia. This is the first time I've heard of it. My massive red flag rises as soon as I hear you mention a wire mesh conveyor. We've had experience of this in the industry, and there's a well-known company who love wire meshes, and the fact that you said that the Russians have, you know, there's a lot of proprietary technology about getting the airflow correct. I can well believe that, because I think wire mesh you've got to treat with a lot of caution, and if you don't get it absolutely right, that's where your problems are going to be, in the maintaining of that wire mesh. So yeah, I've no doubt that it'll work, because a wire mesh has an awful lot of advantages, particularly the very high open area. And so that's a good thing. Oh yes, and my final point is all of these technologies that you reported a lot of EPMs. Some of them are very good, but my comment would be, why don't we immediately, as soon as we see an EPM, let's say 0.06 or something like that, why don't we immediately say we should have a 2-stage process? I mean, this is what Johan de Korte developed in his fine coal dense media. He you know, that process, which has been very successful in the number of plants in South Africa, relies inherently on the recycle stream. It's a 2-stage process, and that gets around an awful lot of these poor separation efficiencies. So that would be my comment, and I think your yeah. So that would be something I'd like you to comment on. Again, obviously that introduces expense, but we're getting, okay, we probably have a system where we have to have more machines, we've got to have maybe double separation, we've got to have a raw coal stockpile, but the operational costs, I would fully agree. I mean, you know, anyone who knows dense media wet plants and how many pumps there are, and tanks and pipes and everything like that, the inherent simplicity of dry separation has you know, has just got to be great in that. So those are my comments. And a question. Thank you.
Thank you very much, Mark. Unfortunately, I was sort of kicked off there by my network for a while, but I think I caught the gist of what you were saying, and yeah, thank you for those comments. Very valid. Thanks.
Okay, thanks, Mark. Next, we've got Simone. Over to you, Simone.
I was saying, I think I'll follow Mark's footsteps in turning on the video because it's probably more interactive. Prof, the question I have from my side is your winnower. It's the first time I'm hearing of that technology, but I have a question regarding abrasiveness. My thoughts initially would be with dry coal processing and air blowing, that in that box or in that picture that you've shown, what is the abrasive implications of that kind of processing?
That's excellent. Yeah, our tests up to now, we've been using single particles, for example, just putting them through, so you don't have particle-particle interaction. But we have already picked up, even through that, the particles striking the insides of the box. It's not just abrasiveness, but breakage, friability as well. If you have something that's slightly friable, look, if it hits the box once it's landed in its right spot, it doesn't matter. But we certainly foresee that we will have dust generation in there, and therefore, by going for the suction system, you will have to have a dust suction at the end. Now, what you're going to do with that, we've again, being academics, we can afford to have these ideas without trying to prove them. But maybe a dry classification cyclone, for example, might work on the dust stream if you got it out. But yes, certainly. We haven't looked at that, but it is something that we are aware of and that we are looking at. It could be the downfall of the technology. I don't know.
Okay, thank you. Appreciate it, Prof.
Thanks, Simone. I see, Prof, we've got two questions in the chat box. I think the first one is from T. Gauri Charan. What do you think is the future of dry coal beneficiation?
Okay, yeah, well, good afternoon, Dr. Guricharan. Last time we saw each other was in Dunbar at one of your plants in India, and it was such a fascinating visit that we thoroughly enjoyed that, and the hospitality that you showed to us as well. I would appreciate that. Yeah, the future, I think, as we go on, we will be forced into it by all sorts of pressures. As I say, the environmental pressures, climatic pressures, I think we will go there. And as with anything, we can think that it doesn't work now, but once you put your mind to it, you could actually make it work. A lot of technologies were born out of necessity and not because people thought it's a good idea. And even after that, it becomes more and more economic as well. So I'm very optimistic about dry processing. I don't think we have much of a choice. I'm not saying we must change everything now or in the next 20 years, but certainly as we go along, I think that'll be one of the leading technologies. Not the only one, because there are cases. I still believe that there is a case to be made for wet processing, especially fine coal, wet processing. But yeah, I think there is a future. I don't think it's something that's going to go away.
Thanks, Prof. I think we've got the next question from Amy Marie Kirk. If the moisture plays a role and is a limitation in the process, can thermal drying be used prior to the separation, or can an absorbent assisted drying or absorbent assisted drying help? Yes,
she refers to Amy. How are you? One of my ex-students. I'm glad to see you are doing well as well. The absorbent assisted drying is also one of the Coltech projects that we are looking at. Again, we are at a demonstration stage as to this one, and there's been a lot of papers by Marco Leroux is actually driving this. There's been a lot of papers out on that one, and it seems to be a technology that can work very, very well. We just need to demonstrate it. So it can. Once again, the limitations with all of these is capacity. Can we design an absorbent assisted drying plant that can handle capacities? On the other hand, can we design a dry beneficiation plant, for example, winnowing, that can handle the capacity? So yeah, you will have to go. I don't think thermal drying, it's one of these things that I don't think, especially in this country, we do not like it. it's on the table and we know exactly how to do it, but there are all sorts of problems with that one, especially if you go to fine coal. The combustion of fine coal could be problematic. But one thing that we are looking at, and that is certainly something, because you've got pneumatic systems and you're blowing with air in any case, if you can just, I don't want to say heat the air, because we've shown that there's more advantage in conditioning the air. In other words, bringing the relative humidity of the air down. And we've shown before that drying can happen at air of 30 degrees, ambient air, but as long as you bring your moisture content, the relative humidity down to, in the 30 or the even lower than that %. So rather than have a heater on the air, you can have an air conditioner on the air. Once again, we're not talking costs yet. And if you blow that dry air and you use the dry air to affect your dry beneficiation as well, you're killing two birds with one stone. So rather use the air that you use to do the separation, pre-dry that or pre-heat that if you want to, and then you can actually achieve the same thing.
Thanks, Prof. I think the next one is from Richard Hayton. Interesting, we have used winnowing in other minerals such as diamonds in the final sorting, which was traditionally dry. This was done to remove dust, organics, and other light waste matter that could clog the downstream process. I think an interesting comment and totally valid statement. I don't know if you want to comment on that, Prof.
Not really, because the stage that Richard's talking about is in an enclosed box, and once you go in there, you can't get out unless they shoot you because of the technology in there. So this information is not out there, but I have worked with De Beers on a lot of things, so I'm aware of it.
Okay, thanks. I think we've got time for one final question before we wrap up. If not, any final questions? It looks like there's not. So from our side, Prof, thanks very much for the very informative presentation. I think a lot of interesting concepts and new technologies and novel technologies, as you've mentioned. I see a question just pops up as I'm concluding, but let's try and address it. It seems to have disappeared. But we appreciate the effort and the time in presenting this, Prof, and all the novel technologies that you've presented. Just a punt for the universities: if you are keen to do a master's or PhD, you've got some interesting topics to explore and be part of the novel team that looks at that. So please consider that if that's your calling. And finally, once again, thanks, Prof, for your time, and everyone on the call. Thanks for your attendance and the attentiveness and the questions asked. We appreciate it. And the recording will go up onto the SACPS YouTube channel in the next couple of days. Thank you very much.
Thank you. Thank you.
Yes.